Take a look at this image for a few seconds. What do you see? I, for one, switch back and forth between seeing two faces and a vase. Now, try perceiving both at the same time. Are you able to? The odds are that you're not, or at least you're not inclined to. But why is that? Why is this third option of two faces and a vase not taken into account? Why is it eluding our perception? This can be attributed to the theory of Bayesian inference.
Bayesian inference is a way of modeling probability where current evidence and past knowledge is taken into account to predict the likelihood of a hypothesis. This will make a lot more sense with a real-world example. Let's say that a friend tells you a rumor. What's the probability that it's true? Bayesian inference uses past and present data in order to make a decision like this. We need to take three things into account: the probability of a rumor being true, the probability that your friend would tell you a rumor that's true, and the probability that your friend would tell you a rumor that's not true.
Based on your knowledge of your friend and rumors in general, you guess the probability that your friend would tell you a rumor if it's true is 90%, whereas the average person is 30%. You would also assign a probability of 70% to a random person telling you a rumor that's untrue, but only a 20% chance to your friend since they're pretty honest.
This key equation of Bayesian inference, aka Bayes' rule, synthesizes all of these probabilities to find out the probability that the rumor is true, given that your friend is the one who told you. This term, the posterior, is what we're trying to find out. It's the probability of our hypothesis that the rumor is true, given the data, that our friend was the one who told it to us.
The next term, the likelihood, is the probability of the data being true if the hypothesis is. So, what's the probability that your friend would tell you a rumor if it was true? We've established this as a 90% chance, so let's input 0.9 into the equation. The term next to it, the prior, is the probability of the hypothesis being true overall. What's the chance that a rumor you hear from an average person is true? We've established this chance as 30%, so let's input 0.3.
The term in the denominator is the evidence, which looks complicated, but it is just asking us to do the same thing we did with the first hypothesis to every hypothesis, and then add them all together. In this case, there are only two hypotheses. The rumor is true and the rumor isn't true. We already know the term for the first hypothesis since we did it on top, so let's input that.
Now we need to find the second term. The first part is asking us for the probability of the data being true given that the second hypothesis is true. Let's say there's a 20% chance that your friend would tell you a rumor if it's not true, so we input 0.2. The second part is asking us for the overall probability of the second hypothesis being true, so the chances of a rumor an average person tells you being untrue. The chances of an average person telling you an untrue rumor is 70%, so finally we input 0.7.
Now we calculate what we're trying to find. After doing the calculations, the final answer is around 0.66, so there's a 66% chance that the rumor you just learned is true. Let's revisit the illusion we showed at the beginning and examine how Bayesian inference is involved. In this case, the possibilities are either two faces, a vase, or two faces and a vase. The data could point in any direction, so the likelihood of each is equal. The evidence for each is also equal, since it is simply the sum of all the hypotheses.
This is where priors come into play. In your past experiences, you've probably seen a good amount of vases and a good amount of side profiles. However, you probably haven't seen a real-world scenario with two people facing each other right over a vase that lines up with their faces, so the chances of that are very low. So, when your brain is calculating the probability of each hypothesis, the probability of seeing two faces and the probability of seeing a vase are roughly equal, while the probability of seeing both of them simultaneously is much lower due to a much lower prior. Therefore, the posterior probabilities determine that our eyes must be perceiving either two faces or a vase, not both.
The reason our brain relies on inference for perception is that in our daily life, similar to this illusion, our senses don't give us a complete and accurate view of the environment. So we must make inferences based on the limited data that we do have in order to create a more cohesive and helpful model of the environment. This inference is what allows us to navigate through and interact with the world efficiently. Thanks for watching!